Last decade has witnessed the rise of artificial intelligence, and most of the AI models are considered black box because they don't provide insights about their decision-making process. Therefore, explaining AI has been established as a requirement for trust and adoption for high-stake domains. Interesting questions about XAI include: what are the different categories of explainable frameworks? What are the different tools for XAI? And what are some open challenges for XAI? Hello, everyone, and thanks for joining us. My name is Muhammad Rehman Zafar, and I am a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Francesco Bodria and Francesca Naretto. Francesco Bodria was born in 1995 in Parma, Italy. He graduated in physics bachelor degree at the University of Parma and in physics of complex systems, master degree at the University of Turin in 2019 with a thesis on explainability methods for neural language processing, applications in sentiment analysis. Currently, he is a PhD fellow in data science in the joint program offered by Scuola Superior Spiraro Antona, University of Pisa, IMT Lusa, and National Research Council. In particular, he is working on explainable AI algorithms with the group of ERC XAI led by Fosca Gunotti. Francesca Naretto is a PhD student in data science under Professor Fosca Gunotti and Professor Anna Monreal supervision. She is working on explainable AI with the group of ERC-XA led by Professor Fosca Gunotti. Francesca graduated in computer science, a bachelor degree from the University of Turin, master's degree from the University of Pisa. During the master's, she won a scholarship to work on her master's thesis abroad at the University College of London. The topic of the thesis was a framework for privacy risk prediction and explanations tailored for sequence data. Her primary research interest in ethical AI, with a particular interest in data privacy and explainable AI. Francesca and Francisco will be presenting benchmarking and survey of explanation methods for black box models. To the audience, please post your questions in the chat and we will be asking your questions immediately after the presentation. So without further ado, I will now turn the presentation over to Francisca and Francisco. Please take it away.
Okay, thank you very much for the introduction. So I'm Francesca Naretto, and today I would like to present to you our latest work. It is entitled Benchmarking and Survey of Explanation Methods for Black Box Models. And here you can find the QR code. If you scan it, you can find the paper that I'm talking about. So before I start, I would like to introduce to you the authors of the paper. We have Fosca Giannotti, who recently won an IRC grant on explainable AI, then Dino Pedreschi, Riccardo Guidotti, Salvatore Rincivillo, me, and Francesco Bodria, who is going to present with me today. Okay, so let's get right into the topic of this survey. Explainable AI. Explainable AI provides explanations for the decisions of machine learning models. So basically, right now, machine learning models are often seen as black boxes. This is because internally they are so complex and full of functions and weights that it is actually really difficult for the end user, but sometimes also for experts, to understand what is happening inside. What we would like to have instead is the other situation, in which the box is transparent and we can see inside what is happening. So we feed the machine learning model with an input, and we can see what is happening and the internal reasoning of the model to arrive to the output that we have. So there are many positive implications for explainable AI. First off, as I told you, the internal reasoning of the model, we are able to understand them with explainable AI. And this is actually an enabling factor because it allows us to identify bias or in general problems. And this is actually really important because if we tackle these problems and we solve them, we can develop better models. That is actually one of the most important goals for us. Okay, so about the taxonomy. Clearly, explainable AI has been an interesting research area for many years right now. But during the last few years, we have a lot of papers and a lot of interest in it. So the approaches that we may have are kind of divided into two different ones. We may have explainable by design methods. Here, we are talking about models in which the explanation is actually part of the structure. So we have to modify the machine learning model in order to embed the explanation. Clearly, this setting is really interesting, but also extremely challenging, because if we have a machine learning model that is working and we have to retrain it all from the beginning with a different machine learning model, we may end up in problems of performance, for example. So this is actually a challenge here. The other approach instead is the most popular one, and it is about the black box explanation methods. So here, the black box is considered as an entity. We do not want to touch it. So if we have like a machine learning model already trained that is working perfectly, we can use it and we can explain it from the outside. Here we have, like, for example, local or global explanations. Local in the case in which we want to explain just a single record, and local and global instead when we want to explain the overall behavior of the machine learning model. And we may have also model-specific or model-agnostic approaches. Model-specific when we try to assume something about the black box model. Like, for example, I know that it is a neural network, and so the structure is made of layers or of neurons. And instead, model agnostic is the most challenging setting, because we do not assume anything about the black box model and we consider it as an oracle. So we can query it and that's all. So this is actually the taxonomy of explainable AI for now. And I would like now to introduce to you the structure of our survey. So we decided to take a more practical point of view for this survey. And for this reason, the first question we asked was, what kind of input data are we using? This is because clearly, depending on the input data, we may have different machine learning models, and different machine learning models may be able to work with different explanation methods. So for this reason, we decided to divide into sections our survey based on the kind of input data. So we have a section on tabular data, one on images, one on text, and one of others approaches, like, for example, we have ontologies or time series data sets here. Okay, then after this question, we ask ourselves another interesting question, that was, what kind of explanation are we looking for? Because clearly, this is really important. Depending on the kind of input data, we are going to have a different kind of explanation in the end. So for this reason, we decided to subdivide each section into the different kind of rules of features of explanation kind that we may have. Like, for example, for tabular data, we may have feature importance or rules. Instead, for images, we may have saliency map or prototypes. And for text, sentence highlighting or attention-based methods. So this is actually the structure of our survey. And in order to be even more practical, we decided to actually test the available explanation methods implemented in Python. So for this reason, we selected a bunch of data sets, and on them, we actually trained machine learning models to test the available implementations in Python of the explanation methods. So we considered, for tabular dataset, the German and the adult dataset. They are two benchmarking datasets. German one is smaller with a lot of categorical variables. Instead, the adult one is a little bit bigger with numerical variables. And instead, for images, we consider two benchmarking datasets, the MNIST and the Zafar. MNIST is handwritten digits. Zafar instead is low-resolution images in color with 10 classes. And then, as a challenge, we consider also the ImageNet dataset, a big dataset with 1,000 classes and high-resolution images. For text, we consider sentiment analysis, movies reviews, and places reviews. So on them, we actually trained different machine learning models. For tabular data, we consider a logistic regression as a benchmarking, an XGBoost and a CatBoost ensemble models that are a little bit better in terms of performance. And then for images, we consider as a benchmarking a convolutional neural networks with two convolutional layers and two linear layers for the Zafar and the MNIST dataset. For ImageNet instead, we consider the already trained VuGG16. And for text, we applied BERT, actually. So clearly, we had all these machine learning models already trained, and on them we tested the explanation methods available in Python. And what we asked ourselves was, okay, now that we have all these beautiful explanations, what can we do? How can we evaluate if they are really good or if someone is worse, someone is better? So what we decided to do, we understand a little bit more about the evaluation measures. For this reason, there is also a section in the survey about the evaluation measures. I have to tell you that actually there are still a lot of open points in this setting, and so it is really challenging right now. But we can say that we have two main approaches, a qualitative and a quantitative one. So the qualitative evaluation actually aims at understanding if the explanations are usable for an end user. So if the end user is able to understand concretely what the explanation is telling him. Instead, for the quantitative evaluation, well, here we want to understand better the performance of the explainer. And for the purpose of our survey, we decided to test quantitative measures. So we evaluate our results in terms of fidelity. Fidelity is the most popular kind of metric in this setting. It evaluates how good is the explanation method at mimicking the black box. So the idea is that if I have a record and I feed it to the machine learning model and to the explanation model, I would like to have in the end the same label. Then we also evaluate the stability, and the stability aims at understanding how consistent is the explanations. So the idea is that if I have two records that are similar, I would like to have in the end two explanations that are similar, clearly. And then we consider also some deletion insertion methods. Basically here the idea is that I would like to rank my features in order of importance and remove feature by feature depending on the importance of the feature, clearly. So what I would like to have is that if I feed my record without some features into the machine learning model, I would like to see a decrease in the performance. And clearly, this happens also in the opposite direction. So if I insert feature by feature. So clearly, if my performance of the machine learning model are decreasing, it means that actually the explanation method was right, was telling me something that was correct. And here we consider the area under the rock of the predictions of the modified input or the faithfulness that computes the correlation between the modified features. Another important thing that we consider is also the running time, because a lot of the methods that we analyzed are quite slow. So for me, it's all this part, and I would like now to present to you the tabular dataset. Okay, for the data in a tabular format, we may have 4 different kinds of explanations: feature importance, rules, prototypes, and counterfactuals. For feature importance, well, to each feature here we assign an important value, and this importance value represents how much that feature was important for the actual classification that we are looking at. And these kind of explanations are actually really popular. One of the most popular in this setting is SHAP. SHAP presents to you plots like this one. This was from an XGBoost model trained on the adult dataset, and in particular, this record was classified as a class greater than 50K. The blue features are pushing the value lower, while the red features are pushing it higher. Then we may have something like this. This is from Dalex. This is called breakdown plot, and here the red features are pushing the value lower and the green features are pushing it higher. This was a record classified as class less than 50K. And we may also have something like this one that is actually from an explainable by design model that is called explainable boosting machine. Also, in this case, you can see that the 2 different colors are representing the different importance for the classification. Okay, so now moving on to rules. Rules are really important in this setting. They are if-then else statements, and we have a set of premises and a consequence. Clearly, the structure is really human readable, so people really like it a lot. And we may have something like this one that is from Lore. a classifier local and agnostic, or this other that is from Anchor, another classifier, really, really popular. To conclude the tabular explanation kinds, we have also prototypes and counterfactual. Prototype, well, a prototype basically is an object that represents a set of similar records. So we may have, like, for example, a prototype that is the centroid of a cluster, and clearly the record we are trying to analyze is part of the cluster that we are looking at. Or maybe the prototype may be the result of a synthetic generation of records, or an example, for example, taken from the training data. And the counterfactual instead is the prototype opposite. So it tells you what to do instead to have the opposite label. And this is actually something really interesting because it is really close to human reasoning. So also in this case, we may have a generation from synthetic data, or from a referent population, or from examples. So to conclude and wrap up the tabular part, I would like to present to you the comparison about fidelity, faithfulness, and stability. So in the first table, you can find the fidelity and faithfulness. About fidelity, as I told you at the beginning, fidelity tries to understand how good is the explanation method at mimicking the black box model. And so here we can say that mostly all of them are really good. But regarding faithfulness, that is one of the deletion methods in which I can delete feature by feature to see if the performance of the model decreases. Well, the range is between -1 and 1, and I have to say we do not found really good results, even if sharp is better than lime. And the last table that you see here is about stability. Stability, unfortunately, was not really good for none of the methods we tested. And this is something that is still an open point. So to conclude, I would like to present to you a comparison between feature importance and the rules and counterfactuals, because feature importance right now are the most popular kinds of explanations for tabular data. We have fast algorithms and a lot of implementations, but on the other hand, they are really difficult to understand, especially if we think about people that are non-experts. Instead, rules and counterfactuals, well, they are more human readable, and in particular counterfactuals tell you what to do instead, so people really like it. But we do not have a lot of algorithm, and the ones that we have are really, really slow. But I have to tell you that a lot of people are starting wondering about counterfactuals and how to get a little bit more interesting in this setting, so it is an open point right now. For me, it's all, and I leave the floor to Francesco Bodria, who is going to present the part on images.
So hi, everybody. Let's talk about the explanation from the images. So there are three types of explanations for images: saliency maps, prototypes and counterfactuals, and concept attributions. Saliency maps are the most popular explanation for images. A saliency map is an image in which a pixel's brightness represents how salient the pixel is. The greater the value, the more important the pixel will be. To visualize saliency maps, we can use a divergent color map, for example, ranging from red to blue. Let us focus on the image on the left here. The black box predicted hat as a prediction, while the label on the dataset is mask. The error is due to a person in the background who is wearing a straw hat. As we can see, the person in the background is highlighted in red, so it has contributed the most to the prediction of the image. There are two approaches to create saliency maps: pixel value and segmentation. Pixels value, which are the one on the right, assign to every pixel a value, while segmentation, the image in the center, segment the image into different pixel groups and then assign a saliency value for each group. Segmentation methods are more human-friendly, but they have their drawbacks. We tried the 9 different methods for saliency maps. We tested the methods on 3 different datasets, NIST, Zafar, and image, as explained before, to have all the possible image type, ranging from black and white images, the first 3 from the left, low resolution color image, the 3 in the center, and high resolution color images from ImageNet, the 3 on the right. In the segmentation methods, the segmentation parameters are crucial for a good explanation. This is especially true for low-resolution images, where the segmentation fails, and we only found one group of pixels with a very large value. We have found also that the black box trained on the Zafar dataset is looking at the background. Our dataset has a bias. All the deer class images are on a grass background. So the black box is using this to exploit the problem. All the methods have found their of the hat presented before, but for high resolution images, we have very different explanation among methods. So this could be a problem, but this is because the more information we have, the more complex the problem is. So these problems are the kind of problem useful not for the final user, but for the expert who has built the black box. Science maps are great for debugging, not for displaying to the final user. We compare the silencing maps using the insertion deletion matrix. We observed that segmentation methods are better with big images, and among the methods tested, Rise seemed the better due to its hybrid approach, which uses segmentation, but it's kind of pixel-wise on a very broad range. Another things that we have found is that the guided methods are not good for silencing maps explaining. Most guided methods use the label of the dataset to increase the explanation. In this example, we have on top the tested images, as before. In the center row, the explanation produced only using the gradient of the black box used, which was a CNN. At the bottom, and neural network, at the bottom, we have the explanation produced by a method called smoothgrad, which is a guided method which we use the label of the data. We can see how the values are moving towards the subject of the image. So this is not what the model is looking for. As human, we only look for what we think is true, but this is not the case. In general, science map have many other problems like this one reported here, and we have reported others one in our survey. So another types of possible explanation is prototype. Prototype is to produce prototypical images that better represent a particular class. This is better since human reasoning is often prototype-based. We use a representative example as a basis for categorization and decision-making. However, this type of explanation is difficult to compare and difficult to produce. Here we have two examples. On the left, we have the prototype produced for this 5 image. Yes, it is a 5. Our model is looking for a 4 instead of a 5 because it has learned that the 4s have this very particular pattern, which is similar to the image we tested. This is the other way people write 4s. On the right, we have images produced by the algorithm called MMD Critic. We observed that our dataset has another bias. Airplane, this time, are on a sky background, which could be a problem for the classification of other classes, like birds, for example. Counterfactual instead are different from prototypes, but also similar. They also produce samples of images similar to the original one, but with altered prediction. Some methods output only the pixel variation to the original image, others the whole altered image. On the left, we have the same image as before, the 5, and its most similar variation with a different prediction. We can see that the hole in the top has contributed to being a 5 and not a 6, and the not closed loop on the top of the number to not be classified as an 8 or a 9. On the right, we can see that the counterfactual airplane is on a white background, highlighting these facts of background evaluation of our black box said before. Last method for explaining images is called concept attribution. Most machine learning models are designed to operate on low-level features like edges, line in a pictures that not correspond to high-level concepts that human can easily understand. Concept explainability constructs the explanation based on human-defined concept, rather than representing the input based on features or like lines or some internal states of the model. For example, concept attribution can quantify, for example, how much the concept stripes has contributed to the class prediction of a zebra. These types of methods are very new to the literature, but they are rising. The problem with these explanations is that human intervention is needed. They are human-defined concepts. So the user has to select many images belonging to a concept and feed them to the method. The model then quantifies the concept, how the concept defined by the user has contributed. In the example reported here, we can see that the eyes and the hockey player have contributed to the final prediction of the image, but not the fonts in the background. However, as we can see before, that some methods like GradCam are highlighting the stance as important. So this could be a problem because our methods is looking at the stance, but and not at the right things. So the last, yes, this is what's the problem. The last type of data is text. Text is more complex and structured than other data types, and it is more difficult to explain. We tested the methods on a sentiment analysis task. The model has to recognize if a sentence is good or bad, like Amazon reviews. We have sentence highlighting, attention-based, and other miscellanea of methods. So sentence highlighting is a science maps, basically, applied to text, and consists of assigning to every word a score based on the importance that the word had in the final prediction. In the example, we have tried three different methods that support this type of explanation test as before for images. We added the fourth one, which is just the gradient multiplied by the input. We can say that it is a sort of baseline. Intgrad and Lime are better than Deeplift to capture the most meaningful words in this negative sentence, like sucks, ate, and so on. Very bad. For comparison, we have also used the deletion insertion metrics. For both metrics, we have a very poor performance among all the methods. However, when dealing with text, removing a single word barely changes the meaning of the sentence. So this could be a problem of very poor performance among all the methods. And we have attention-based methods. Attention-based methods show through an attention layer which part of the image contributed most to realize the label. So this value can be interpreted as the probability, the attention, that a word is in the right place to focus on predicting the next word. An attention layer is a type of layer put on top of the model, which captures this correlation among input words. However, it's not clear if this attention methods helps gain interpretability, and what are the relationship with the model output. Finally, we have tested anchors and this framework called Quint. Anchors is similar to sentence highlighting, but it also provides some sort of prototype and counterfactuals, while Quint has a different approach. It uses an interactive framework to provide to the user different explanations, and it is the user who will decide which explanation is better for him. So in the survey, we have tested other methods of data. We have not to consider here, like ontology and time series. Sometimes in a dataset, we have an ontology tree, and we can use this information to create a better perturbation of the data and provide better explanations. Time series instead is an interesting data type, but it's the most complex to explain. This survey is only for them. A typical approach is to return an exemplar, a counter-exemplars time series, or also called shapelet-based rules. For example, a rule could be if this pattern or this shapelet are present and this other not, then this time series is classified as Y. We have done our experiment using very different toolkits from IBM to Google. Some toolkits, like the Facebook one, only works for PyTorch model, other only for TensorFlow models. Other are good for matrix, other for tabular, other for images. So we have a lot of diversity. And since of this diversity, we thought to build our library, which includes all of them. But for now, it's only under development. So thank you very much. And if you have questions, please ask.
Thank you, Francesca and Francesco. Now we will start the QA session, and we will be presenting our speakers with live questions as well as questions we had received in advance. So the first question is, how can we quantify the quality of explanations?
Okay, this is actually part of the things that I was talking to you before. It is quite challenging right now to quantify the quality of explanations. This is because actually we do not have a common ground. A lot of people have different ideas, and so, for example, there is an interesting paper about of Bin Kim and Doshi Velez. They talk about different analyses based on functionally grounded and human applications, but clearly this is mostly for the end user experience, let's say. I think that one of the most interesting areas right now is about ground truths. This is because actually there is a recent paper that is called Evaluating Local Explanation Methods on Ground Truths. Basically, the idea here is that if I have an explainable by design method, so something that is intrinsic explainable, I can have this one as a ground truth on which compare the results of explanation methods like black box models. And I think that this is actually one of the most interesting research areas right now that may actually give us something that is equal for all of us and on which we can actually test the actual godness of explanation.
Okay, thank you. And the next question is, what different models, with different models, how can we decide which model generates accurate explanations?
Okay, well, this is not an easy question, actually, because clearly it depends, first of all, about the final user, because depending on the kind of user that we want to present the explanation, we may have different explanations to provide. Like, for example, if we have experts, well, then something that is maybe quite difficult to understand at the beginning, but with a lot of details, it's really good, because clearly they want to understand it perfectly. And instead, if we have non-experts, well, maybe then a more abstract explanation, but that give us some insights about the reasons, then it's good. This is one, and clearly the other one refers to the problems of quantify the goodness of the explanation that I told you before. So actually, there is work to do and open points on which we can actually work. So it is good for us, but for now we don't really have a clear answer to it.
And what are the few evaluation measures that you think are good for evaluating an explainer?
Okay. Well, for sure, fidelity is really important, because if our explanation model is not behaving similar to the actual model that we want to explain, then we have a problem. So this is a key point, but also the stability is crucial, because clearly we would like to have something that is behaving the same all the time without changing it. Otherwise, how can I be sure and how can I trust it? And this is actually one of the major problems here, the trust on explainable methods. Then I think that the thing on the ground truth that I was explaining to you before is also something that may be really interesting and a crucial open point right now, because if we can have like a ground truth in this setting, we can start understanding the same language and comparing the things with respect to a thing that is actually there and it is established. So
Okay. Similar to stability, we have a question can you please expand on how you measured stability?
how I measure stability?
Yeah, how you measured
Oh,
stability.
okay, yeah. We did it exploiting Lipwitz constant. So basically, the idea is that I take two records that are similar, okay, and I take the two explanations, okay, and I see the difference between them, and I divided it by the difference on the actual record. So the difference of the explanations divided by the difference of the actual records, and then I take the maximum over clearly a great set of records. This was how we did it. There is the reference paper, however, in our survey. It is not part of our work.
So you are computing stability between similar instances, similar data points.
Actually, yeah, not really. I mean, the idea was that one, and then we consider all the test set actually. So since we divided by the actual diversity on the records, this was actually something that we can measure independently of the diversity of the records because we are taking it into account in the formula.
Okay, thank you. And we have seen references to Lime and Sham being vulnerable to adversarial attacks because of their sampling approach. What are your thoughts on it?
Yeah, I've seen this paper. Yeah, in this paper they built a model to fool Lime and Shap. This model generates some out of sample the points, very similar to the Lime one, and then if a point is out of sample, then we propose the right classifier. The right classifier. But then, if the points are in sample, then we choose the biased one classifier. So I think that these methods like Lime and Shap are built for good black boxes for now, and they have to be tweaked to deal with this kind of black box problems. Because for now they are not considered or taken into account. I think that you have to change the perturbation to not produce out of sample data, or with points, or maybe insert a parameter to choose to let the user choose the distance of the points from the original one. Or another interesting approaches could be generating points near the boundary decisions. So here, then it would be interesting to generate some explanation like that. So, yeah.
If I may add something, clearly they exploit the fact that the probability vector is different depending on the fact that the data are from the same distribution as the training dataset or from a distribution that we generated using Lime or using Shap. And I mean, yeah, this is a problem, but at the same time, we can query the black box and we can have the probability distribution. So we can organize better our neighborhood generation and fix the problem in this way. I mean, clearly is an open point and just an idea, but I think that we can do something about it.
Okay, thank you. And another similar question is how can we use XAI for stopping adversarial attacks?
Use
XAI for stopping adversarial attacks.
Yeah, adversarial attacks. I think about images now. Are very, very difficult to tackle with, because especially when we have very big images. So for now, there are a lot of methods like using the mean or passing a lot of images to the methods when training it with also some noise. So this noise or this adversarial attacks is not a problem. Then there are new papers which using some custom loss to create ad hoc adversarial attacks. And I don't see where explainable AI could solve this problem, especially because we are highlighting some part of the images which has contributed. So maybe with silencing map, when we have a very broad range of values in all the images, then this is a symptom that our model is subjected to adversarial attacks. So we cannot solve them, but rather maybe identify them. And then we can work on the training to solve this problem.
All right, thank you. Can you help us understand the difference between Anchor and Lorry?
Yeah.
Yeah. Okay. They are two approaches tailored for tabular data, even if Anchor is also for text, actually. But anyway, the idea is that they give us, as explanation, rules. But the process is quite different, because Anchor exploits a random synthetic generation of the neighborhood, okay? And then, since they can generate a lot of things, they use a bandit algorithm, multi-arm bandit algorithm to generate it better. But then they also use a bottom-up approach with a beam search in order to prune and decide what kind of anchors to maintain and what others are not important or not that important, let's say. And instead, Lore it has a completely different approach, because it exploits a genetic algorithm to generate a synthetic neighborhood around the record that we want to analyze. And then it uses a decision tree, so a kind of intrinsic explanation method. It prunes it in order to have it the small possible explanation kind, and then it retrieves the explanation from them. So it is quite different. So Anchors also has other approaches, because Anchor said that every anchor, if the anchor is okay, so we can apply it, then whatever we change that is not part of the anchor, it's fine, and we are going to have the same classification at the end. And this is actually a crucial thing that Lore do not have for the kind of output and the kind of rules, let's say.
Thank you. What are your thoughts on choosing the right explainer for a problem?
It depends. So on many factors, actually. It depends on the final user and what you want for an explanation. But basically, first of all, you need to choose an explainer that supports your type of data. Then you move to the type of explanation you want. You maybe want an explanation for an expert user or for the final user. You want some explanation of the decision, or maybe some information about where the model is looking for. Finally, you test all the methods that you have selected with this type of explanations with some metrics on your data. Generally, it's better to test multiple methods and also provide to the final user multiple type of explanations, so the user can decide which explanation is right for him, if you wanted to provide an explanation with your model.
Thank you. Could explanation sometimes be misleading or lead users to develop a false sense of confidence in a machine learning system? What are your thoughts on it?
Yes, there is a very interesting paper called Sanity Checks for Silencing Maps, and which shows us the problem of guided methods and in the silencing maps. So basically, these methods were developed to produce better explanations, but using the labels, they introduce some sort of problems, and then in this paper they show that also with modifying the weights of the black box, the methods always show the same explanations, and this is very problematic. So yes, explanation could be misleading. If there are misleading, you can try different explanations to see different methods to see if all the methods show the same thing. Then you can move to other things like produce an explanation with very similar images or very similar data and see what happens. But in general, yes, what you see from explanation is not always what you want to see, but you should be what the model is looking for. So using a metric to evaluate if the features explained are really important. So if I delete him, then I have a drop in the performance. It's always needed, I think.
Okay. So there is another open-ended question. So if you run multiple explainer tools and get different or contradicting explanations, what would you recommend as an approach to choose an explanation?
Well, not an easy question, actually. Clearly, if they have contradictions, it means that something is wrong. So one of them, we have to understand which is wrong and which other is better. So I think that right now, the evaluation measures that we have are not enough to understand what is the best one. Even if the approach on ground truth that I was talking to you before, well, I think that is the most reliable one for now. And also the fact of the stability. I think that it is a sanity check to do every time, because if the model is clearly unstable, for sure we may have contradictions by the same model. So it's pointless to use it, because clearly if we run it 20 times and we have 20 different explanations, which one is correct is difficult to understand.
Yeah. Thank you. This stability was not good for all approaches. Is it because of perturbation? What are your thoughts on it?
Yeah, especially for tabular datasets, the problem was the perturbation kind, because for Lime we had a synthetic random generation of synthetic records, and instead for Lore the stability was a little bit better because the generation is genetic. But anyway, I mean, there are still open points on it, and in particular for Lore we are working to make it stable by exploiting other kinds of generations and also other kinds of stability measurements. So we are trying to understand it, but yes, it is a problem, and especially for the end user, we have to present something that is stable, and if we have the same record in input, we should have the same output. This is for sure something that we would like to have.
Okay, so if we run Lime on one instance multiple times, it produces different explanations mostly in most of the cases. So is it the case with Lore as well?
Not really. This is because Lore uses a genetic approach, so we do not have a random generation, and so they are more closer one to the other, but clearly the genetic approach may end up in a branch that is similar, but in some part different. So that is the reason why we are not completely stable.
Yeah, there is a chance we can get different explanations.
Yes, exactly.
All right, thank you. And the next question is from the live audience. Like, the choice of explainability methods should depend on the application. In which applications would you not use SHAP? In your opinion, what could be improved about SHAP?
Okay, well, I have to tell you that right now I'm seeing a lot of works in which SHAP is applied, and also in industry, a lot of people are starting using it. And I think that the idea, the mathematical idea behind SHAP is really good. They had proposed something really, really interesting. However, the presentation of the plots for the local explanations they are quite difficult to understand, in my opinion, if we are talking about people that are not experts, because we have a base value, then we have a output value. So what is the base value? People have to understand it, but it is actually the mean of different trials with different features. It's not that easy to understand for a person that is not really interested into the topic and is not reading the paper from the start to the end. So I think that yeah, there are a lot of possibility with SHAP, and right now is one of the most popular approaches, and I understand why, because the mathematics behind is really interesting. But in my opinion, we can do better with the final presentation of the explanation, especially for end user, like simplifying it, making it more human readable.
Yeah, if I may add something, one of the thing is speed. SHAP is very slow as compared to other approaches as well.
Yeah.
So
That
speed
is
is
also really true. Yeah, especially if we use a kernel SHAP, that is the one that is agnostic and you can apply it to every kind of machine learning model. It is extremely slow.
Yeah.
It is a
Especially
problem.
when you use when you have a lot of data.
Exactly.
Because it's yeah.
So the next question is similar to this. This question was asked by another stream owner who is actually the owner of this stream, ML interpretability. So since some of the explainers methods are slow, what is the size of the sample you use to benchmark your explainers?
Okay, it actually depends on the experiments that we conducted, because we tried some of them with a bigger data set, but we had problems. And so, like, for example, for Lime, it was not a problem. We can also have like 1,000 elements and it was fine. For others, instead, they took like 3-4 minutes for each record, so it was really difficult to do it. On average, we tested 200 elements for each kind of data set, plus the explanation that we wanted to use, depending on the machine learning model, clearly. So we had different models because, for example, for the tabular data set, we had in total 6 different models. So 200 for each of them.
If I can add something, when using SHAP, we have using k-means before on the data to speed up some calculation, but it was really slow, especially when creating a very large neighbor.
Yeah, and also using SHAP for tabular data, we can apply like linear SHAP and also tree SHAP. They are faster, so that is something good, but at the same time, they did not provide the same output as the kernel, because I don't know if you're aware of it, but for example, the linear kernel is returning just one array, in which we have just the importance for one case. And instead, the others are proposing to you one array for each class. So this is also something that I think that in the future has to be tackled better, because we had a problem in comparing the things, because we do not have the same result in the end.
Yeah, and also tree explainer is the model specific, so it is not model agnostic.
Yeah.
And that
Only
is
for
also
trees.
the problem. Only for trees.
Okay. The next question is, in some works like Samik et al., prototypes are considered to be more about interpretation than explanation. How do you understand explanation and how interpretation?
Okay.
Yes.
Well, it's a difficult question, because right now, in the different papers that we saw, there were so different considerations about interpretations and explanations. Everyone, the different labs, all of them has their kind of analysis and their kind of concepts, and we do not have a common ground on which we can start. So in my opinion, clearly the prototype is a kind of interpretation. But at the same time, I think that for the end user, if we are considering a setting in which we want to propose the prototype as an explanation for the end user that has to understand the reasons why he has been classified as, I don't know, like, for example, high risk for this particular thing, I think that it can be okay, even if, yeah, it is more, I think, a kind of interpretation.
Yeah, if I can add something, there is a paper called This Looks Like That from Cynthia Rudy. And in this paper, they built called ProtoPNet, which exploit things in bird dataset, if I remember correctly, about yes, this image is of this particular bird because this part is similar to the other one, this part is similar to this one, and this looked like this other one. So
yeah, go ahead.
Yeah, and so in this way, prototypes can be used as explanation of a black box. Yeah, and which using part of the image which are similar, I think.
Okay.
So
But
this was very interesting.
is it concept whitening paper you're talking about?
Oh no, the paper is called "This Looks Like That," exactly like this.
Okay. All right. Thank you. And the next question is regarding counterfactual explanations. How can you evaluate the quality of counterfactual explanations?
Okay. So, considering counterfactuals, clearly the problem is that you have to understand the actual dimensions in which you are able to work for counterfactuals, because it's not that easy, since if you have a rule that is telling you, okay, your age is less than 25, so I'm not granting you a loan. Okay, perfect. But if my counterfactual is your age should be less than 0, okay, then it's not going to work properly, because no one can really have that age. So for counterfactuals, I think that one of the most interesting setting may be to actually try to understand the different constraints of our data set and test them against the counterfactual to see if we are still in something that is possible, in the available possibilities of our actual data set. So this is something that we didn't find in a lot of papers, just maybe hints and suggestions, but not really something done. But at the same time, I think that it is the only possible way in which we can evaluate the goodness of counterfactuals.
Thank you. So the last question is it possible to contribute to the development of the library you mentioned in the end? So this question is from the live audience.
For now, the libraries is private only to our lab, because it is in a very early stages. Yeah, but we are planning to extend him when we arrive to a base that we think is good to be public. Then we can extend also the integration of our methods produced by some other research group and integrate them in our library.
Yeah,
so before we just want to build some base to work on. Yeah, but it will be available soon.
Yeah, we are working on the structure right now, but
exactly.
The idea is that after having the structure, well, every kind of method that arises is perfect. So whoever wants to contribute and add his methods, well, that's perfect for us. So the idea is that we would like to have something in which people can insert a record and see the different explanations with the different methodologies and have a comparison like on the fly. So more models, better it is.
Yeah, thank you so much. Before we wrap up, are there any final thoughts that you would like to share with us?
I think that we cover basically everything that is in the survey. Clearly, there are some things that we just mentioned and some methods that are there, but we don't talk about it. But overall, I think that the take-home message is that we are working on it, and there are really interesting approaches right now, even if there are a lot of open points, especially in the evaluation of the goodness of the explanation. So I think that that's all for me.
Thank you.
I think that there are a lot of methods in the literature, and there are new one every day that provides some sort of explanation, but not so much are providing some sort of evaluation of their methods. And qualitative evaluation, like see the example, we've seen the right things that it's not working, may not work along. So maybe it's better to provide some metrics, which is quantitative, and that can show, your method is really good. And I think this is the right direction of the research now.
Thank you. Thank you so much. Francesca and Francesco, I congratulate you on a significant contribution to the field, and I thank you for a great presentation, and we thank all who joined us online. To see more free content like this, please visit our website at ai.science and log in to access slides from this and other sessions. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. This concludes our event. Thank you for watching.
Thank you for inviting us. Thank you. Bye.